Here are solutions to homework set number 2 for ECE 376 Embedded Systems. This homework looks at assembler and flowcharts. So the first problem is, given a list of assembler commands, what happens? So assume I've got two spots of memory called A and B and my W register. The initial value is 12, 9, and 3. After each command, what's the contents of W, A, and B? Well, the first command says add W to A, put the result in W. So 12 plus 9 is 21. The result goes into W. A and B stay unchanged. The second command is it says take W, add it to B, put the result in B. That's the difference between comma W and comma F. W says put the result in W register, comma F says put it wherever on whatever register you're operating on. So 21 plus 3 is 24. Result goes in B, 24. W and A stay unchanged. Now do inclusive OR. What is A or W? Put the result in W. So I've got 21 or 9. This is a bit operation. So 21 in binary is 0001, 0101. Here's 9 in binary. Go bit by bit. If either bit is a 1, the answer is a 1. So here's the answer. That corresponds to 29. So 21 or 9 is 29. No one else can figure that out, but if you go bit by bit, kind of makes sense. AND operation. Take W, AND it with B. So what is 29 and 24? So again, you got to go bit by bit. Here's binary 29. Here's binary 24. Go bit by bit. If both bits are a 1, the answer is 1. Otherwise, it's 0. Gives you this answer. 29 and 24 is 24. Move 6 to W. So W becomes 6. A and B are unchanged. Subtract. What this does is subtract W from A, put the result in A. So 9 minus 6 is 3. Put the result in A. So that's kind of how the assembler works. It goes line by line. Each instruction just does one thing. Problem 2. Convert the following code to assembler. So this is C code. If I have an unsigned character, those are 8-bit variables. I first have to define where in memory do you store A, B, and C. And arbitrarily, I'm going to put them at memory locations 0, 1, and 2. You can actually put these anywhere you want. You've got 3,900 spots in memory. Pick 3 spots. To do 2 times B plus 3 times C plus 4, some things that seem kind of stupid actually make sense in assembly. To do 2 times B, what I can do is add twice. So move B to W, add B to W, that's 2 times B, put the result in W. Now add C once, twice, 3 times, I have 3 C's, add 4. There's your 2B plus 3C plus 4. Take the result, move it to A. So that's one solution. Not real fancy, but it works. There is a multiply command. You could also do this using the multiply command. So again, define A, B, and C. I've got a dummy variable called X, which I guess I'm not using, so I don't need that. I first multiply B times 2. So move 2 to W, multiply W times B. When I do that, the result goes to 2 other spots of memory called product high and product low. Just take the low 8 bits, move it to A. So that's A is now 2 times B. To get 3 times C, move C to W, multiply by C. The result goes in product high, product low. Move product low to W, add it to A, put the result in A. I now have 2 times B plus 3 times C. Move 4 to W, add it to A, put the result in A. I now have plus 4. That's another solution. In assembler, there's many ways to do the same thing, as long as it works. So that was 8-bit operations. 16-bit operations are a lot harder because this is an 8-bit processor. To do 16 bits, it's kind of like the same thing to do in decimal. If I say, what is 76 plus 95? I go right to left. First say 6 plus 5 is 11, carry. 9 plus 7 is 16, plus 1 is 17, with a carry out. So there's the addition. Go right to left, digit by digit. Same thing in assembly. If I have a 16-bit number A, B, and C, I've got 2 bytes, 16 bits. If I call this A, and this location A plus 1, there's the low byte, high byte. I need to first add the low bytes together, then add the high bytes with a carry. Same thing I did in base 10. So what I'll do is 2 times B. Move B to A, so there's the low byte of B, the low byte or high byte of B. Now add B to A. Start with the low byte, move B to W, add the low byte of A, done. Store it in A. Take the high byte, move that to W, add with carry to the high byte of A, put the result in A plus 1. That's 2 times B. Same trick, now take C, add it to A. Oops, that's just an A. Add it to the low byte, add it to the high byte with a carry. Once, twice, 3 times. Now take 4, add to the low byte. 0, 4 is actually the number 0, 4. 0, add to the high byte with carry. And then you have it. So that's a 16-bit add. And kind of note that 16-bit operations are a lot harder than 8-bit operations as an 8-bit processor. Problem 4. Convert the following code to assembler. This is an if statement. So when I say if A equals 0, first thing I have to do is define where A and B are located. I just stuck them at address 0 and 1 arbitrarily. To AND A with 7, I'll move 7 to W, and W with A, put the result in A. That's A is A and 7. Now check if A is equal to 0. I'm going to use the compare skip if equal command. I first have to set it up. So to do that, I want to compare A to W, move 0 to W, that's this part, compare A to W, skip if equal. If I don't skip, I want to go to the next command, go to L1. If I do skip, it's equal, I want to increment B by 1. Next part, if A is equal to 1, increment B by 3. So I'll first move 1 to W, compare A to W, if A is equal to 1, if so, skip. If it's not equal, I'll jump down to label 2. If it is equal, I'll move 3 to W, add W to B, put the result in B. Next one, if A is equal to 2, same trick, increment B by 5. If A is equal to 3, 3, compare, add 7, done. Problem 5 is a flowchart. This is kind of what you'll see on the test. The way I grade the test is block by block. If you have no idea how to do this block, just do the rest. Each block is worth the same number of points. And kind of arbitrarily, I stuck labels at the beginning of each block. That way you can see how the code corresponds to the flowchart. The first part is I want to make port B input, port C and D output. To do that, I move FF to tris B, move 0 to tris C and D. 1 means input, 0 means output. So all bits on port B are input, all bits on port C and D are output. First label. I want to keep looping as long as port B pin 0 is 1. So in a test, bit test skip if clear, port B comma 0. So if it's a 1, I want to keep going. If it's a 1, I don't skip, I keep on looping. So that works. If it's a 0, I skip out. If it's 0, I'm down here. I want to keep looping if it's not equal to 1 or equal to 0. So that's a bit test skip if set. Port B, bit 0. On a 0, I don't skip. I keep looping while it's 0. When it goes to 1, I skip out. There's my rising edge. So right here's the rising edge. Get to label 3. I want to count mod 12. So it goes 0 to 11, 0 to 11. And there's a couple ways to do that. I'm going to say if port C is greater than 11, I'm going to clear it. So I'm going to increment port C, put the result in port C, then check, is port C greater than 11? Move 11 to W, check. If port C is greater than 11, if so, skip. If it's greater than 11, I'm going to clear port C. Otherwise, I don't skip and jump to L4. at label 4. I want to test port C if it's equal to 0, 5, 7, or other. For the first one, for 0, I'll move 0 to W, compare skip if equal to port C. If it's equal, I skip. Jump to label 5, otherwise go to the next test. Move 5 to W, check to see if port C is equal to 5. If so, I skip. Go to label 6, otherwise do the next test. If port C is equal to 7, I skip, go to label 7, otherwise go back to label 1. That's up here. Label 5. Move 3 to W, move W to port D, go to label 1. Label 6. Move 0C to W, move W to port D, go back to the beginning. Otherwise, 0.3 to W, W to port D, back to label 1. So that's the flowchart going to assembly. And the last one is kind of doing an SPI clock. What the SPI clock does is I've got my data line, or my clock line. There's my clock. I've got my data line. So I want to send the number 100. So there's 100. And chip select. If the device is selected, every clock, I'm going to clock in the data. So here's the flowchart. This you don't really have to know to do the homework, but that's kind of where it comes from. Convert the flowchart to assembly, and it goes block by block. So this guy right here is the first part, same as the previous problem. I want to initialize port C to 0. That's that line of code. First label. Keep looping as long as port B pin 0 is equal to 1. So if it's equal to 1, I don't skip, I keep looping. Label 2. Keep looping as long as it's 0. If it's 0, I don't skip, keep looping. At this point, I see a rising edge. So here's my rising edge. On a rising edge, I check, am I selected? And actually, chip select, I guess chip select goes low for this one. If it's selected, in this case, if port B pin 1 is equal to 0, I keep going, otherwise ignore, wait for the next rising edge. That's right here. I want to check bit 1 of port B. If it is set, I got this backwards, it should be clear. If it's clear, I keep going. Otherwise, if it's a 1, I reset. If it's a 1, I don't skip, and I go back to label 1. Then I get to label 4. I want to shift left port C. That's rotate left port C, put the result in port C. Then either shift in a 1 or a 0. Check the data line, port B pin 2. If it's a 1, input a 1, otherwise input a 0. I'm going to do a bit test, port B bit 2. If it's a clear, I skip. So 6 is a set. This is a clear. If port B pin 2 is a 1, I'm going to set port C pin 0, otherwise clear it. So it's shifting in a 1 or a 0. That's your flowchart. That's a software SPI clock. So that's homework set number 2 for ECE 376. And kind of note, assembly is pretty darn cryptic. There's just no way around it. That's part of the reason we only spend 4 weeks on assembly. It's just hard to use. With assembly, I can get lights to blink, I can build a piano. Kind of hard to do anything else. If we want to do more in this class, which we do, we're going to switch over to C. But that'll be after the first test. But anyway, that's homework set number 2 for 376.